debris.
You should click it there.
Okay, so welcome to this week's Origins Colloquium. Actually, I have two talks this week. First, on Monday now, we have Margaret Meixner, who's visiting from JPL. Margaret received her PhD in 1993 with Jack Welch from UC Berkeley, and then immediately got a faculty job at Illinois. So went to Illinois for several years before moving to Space Telescope, where she was working for a number of years, mainly on James Webb Space Telescope.
Yeah.
In 2020, she became the director of SOFIA in the last years of its mission, and then now is head of the section in the Astrophysics and Space Sciences group at JPL. So it's a great pleasure to have you today, Margaret, and we're looking forward to your talk on both the star formation aspects and PRIMA.
Yes, well, thank you, and thank you, Jonathan, for inviting me. What I'm going to talk to you about today is results from star formation at low metallicity that I've been doing with James Webb. And the results I'm going to talk about are product of a lot of the GTO. So I had 60 hours of GTO time, and I focused a lot of it on star formation at low metallicity. And the players that are listed here by name are kind of like a core group of them, but we have several much more extended GTO teams.
Margaret, I think you're on mute.
I am on mute.
No, you should.
Can you hear me?
Yeah, we can hear you.
Oh, okay. All right. And then I'll also talk, so half my talk will, actually most of my talk will be on the star formation, but then I will also give an overview of the PRIMA proposal, which is part of the protocol submitted it a year ago, and we're supposed to hear by the end of this year who moves on to step 2. And that's PRIMA, Probe Far Infrared Mission for Astrophysics. There we go. Okay, so why do you want to study star formation at extragalactic star formation at low metallicity? And part of the reason is the metallicity. Most of what we know about star formation is Orion, Taurus, lots of very detailed studies, and you get into like the detailed physics of what's happening. But then most of the star formation in the universe actually happened at a much lower metallicity and a very intensive phase of star formation. So the peak epoch of star formation, the metallicities were close to 20% solar, and they were also just wildly active, lots of UV. And the nearby star formation fields actually don't reflect those conditions. But if you go extragalactic, and I think earlier you were talking about low metallicity in the outer galaxy, you can do that too. But the advantage of going to places like the Magellanic Clouds is you also get these really kind of bursty star formation regions. And so the study and results I'm going to show you are from 4 regions in the Large Magellanic Cloud, which is half solar, N79, and then actually just skipping over distance-wise to NGC 346, that's 20% solar, and 6822 is 0.2.3, depending on where you read, and then much further away, but very much lower metallicity at 0.03, so these ones with the 18. And the thing about James Webb, it's the first time that we have enough angular resolution and sensitivity that you can do infrared stellar population studies in these more distant sources. And the other advantage is that, these galaxies have known distances. And so, part of the issue you have in the Milky Way is how far away is the object? And then its luminosity. And so in places like the LMC, the SMC 6822, 1 to week 18, we know the distance. People actually, these are pretty famous objects. They spend a lot of time figuring out the distance to these objects. And so you can do comparative studies, the luminosities of the sources. And then also in these regions, things get super luminous. You see superstar clusters and things. And then because they're far enough away, you can, when you image them with James Webb, you get hundreds, thousands of sources. You get a lot of statistics when you do this. And James Webb is super efficient. And so, in a couple hours, So I don't know why there isn't more star formation studies done, because it's super quick and cheap and you get incredible data. And so, basically the synergy with James Webb and ALMA, you can do kind of, and HSC, you can do Milky Way-like studies, sort of Orion, T-Tauri, and Taurus region studies, but in the Magellanic Clouds. Probably don't have to show this slide to this group, but just to kind of refocus ourselves, and this is also how we do the identification of the young stellar objects, is they have different stages of evolution, and on the far right here are basically the cartoon of what's happening, or what we think is happening to the star. The star first coalesces out of gas coming in, that's sort of a class 0. You really find those things with ALMA, things like that. And then you have class 1 where the star's formed, you have a disk, you might have outflows. When it comes to massive stars, certainly they turned on fusion by that point, but the lower mass maybe not. Class 2 is you pretty much have the disk left. Those are kind of the T-Tauri or pre-main sequence stars. And then class 3 is things start dissipating. And so with Spitzer, and this Remy, who's in the room here, we did a lot of work on finding YSOs with Spitzer. Those were really massive sources. They were 5, really more 8 plus solar mass. But with James Webb, you can really get down to solar. And so the goal of my studies was to get down to solar mass, young stellar objects, going from T-Tauri, basically class 2 to class 1. And also with Spitzer, we mostly found sort of class 1 objects. And then, of course, in the middle are the SEDs, and that's where the photometry of James Webb and stuff and the identification of the sources come in. So I'm going to just talk about some of the results. So superstar cluster is born. The Large Magellanic Cloud, the N79 region, is host to embedded superstar cluster candidates forming superstar cluster H72.97s minus 6939. The serial numbers are Herschel catalog, and basically it's the most luminous infrared source in the Large Magellanic Cloud. And if you were to look at it on a map, it's in sort of a backwaters of the LMC. So it's sort of a perfect candidate for James Webb because it's total infrared. We published a MIRI study, imaging study, and a spectroscopy study, so NIAC et al. 2024. Found 106 young stellar objects. These are all embedded young stellar objects. And then the mass ranges are color-coded. And so one of the things is pink here is actually where the superstar cluster candidate is. And of course, this is the entire region. And pink is sort of basically stars with masses greater than 8 solar masses. And actually at the very center there, is where we took one of the spectra. This box here is the MIRI MRS, and actually this is saturated in the MIRI image, and so the MRS spectra was then used to actually extract photometry, and the masses for those young stellar objects are shown next. And so down below is the Spitzer IR spectrum of this superstar cluster. It's pretty. It has some structure and stuff, but then when you show it with the MIRI MRF, you can see you pull out a lot better contrast because you have higher spectral resolution. And then using the photometry, we were able to find the masses for, we have 1, 2, 3, 4, 5, between, 22 and 40 solar masses, all within this very tiny region. So we feel confident now that this is a forming superstar cluster as opposed to like a single source that has bright. There are a lot of massive stars, and these are just the really embedded ones. And when you blow up in here, I've just blown up Y4. So that's this one here at the bottom, the most massive one. There's just a plethora of lines. And in the NIAC 2024 paper, so there's a spectroscopy paper in which all these are blown up. There's so many lines. We kind of focused on a common denominator of getting using the hydrogen lines to do accretion, like the accretion rate for the stars. but there's a lot you can do. You have iron and argon and neon in emission, have lots of molecular hydrogen lines, and you even see things like ammonia and absorption. And
Sorry,
yeah.
did you say how big the region was?
Yeah, let me see. It's like 3 arc sections across and 2 arc sections kind of half a parsec. So it's, I don't know, maybe between a half or a part to a parsec. Yeah. Jumping on to NGC 346. So this is in the Small Magellanic Cloud. This is the first paper we pushed out. This is when like the data processing pipelines weren't quite operating. When you had GTO time, you were on the bleeding edge, and they reprocessed the data a lot. And the catalog, so that from the initial catalogs, we just did with the near infrared. So on the left is the press release image they did at the Institute. On the right is basically just the 3.56 microns, so that's the pH emission band. And then all of these different types of sources. And you can see that the young stellar objects, the ones that are kind of the more embedded ones, are kind of along the filaments. But this was, this showed that, hey, we achieved our goal. Discovery of thousands and thousands of the kind of more solar mass type of young stellar objects. So that was the big result there. But then Nolan Habel, my postdoc, did a follow-up where he just focused on the MIRI imaging and then trying to identify more young stellar objects. So this is the color diagram we used in the first paper, but much cleaned up compared to the initial result, where we're using the 2 micron, the 444 wide, the 115 wide, and this is one. And Paschen alpha. So this trend up here, which is where we think the young stellar objects are, sort of with and without Paschen alpha, some of this trend actually is really due to extinction. I mean, that you're just, you're getting redder in that direction. And then, we classified the different sources where they land here. But then you can also see them through color magnitude diagrams, whereas the more luminous on the left here at 115, which is the largest catalog. And then here you have sort of the biggest lever arm in color, the 444W, and then this is how the AVs go. And so again, the young stellar objects are here, they're red. They're not necessarily the brightest in these near infrared colors, but they're definitely red from just a star. And then with MIRI, so this is the 7, 7, and the 10 microns. We look at the embedded young stellar object candidates, and basically anything kind of red of this is an embedded stellar object. And this first paper was really focused on trying to select some very sure bets on young stellar objects because we had follow-up spectroscopy to plan. So it's not the most comprehensive paper that's coming, sort of within the next year. But it's to identify things that were sure bets. And so here are the fitted YSOs here with yellow, and those are candidates that we use for the near spec follow-up and the MIRI follow-up. So what is it that the MIRI reveals? So it traces the structure of the diffuse emission from the cooler gas and dust and shows the very deeply embedded young stellar objects. And in the paper, we show that there are 833 candidate young stellar objects, many of which were also flagged with NIRCam. And then here is, basically a gradient in terms of how many tests of color cuts did they pass. And the ones, again, in the yellow diamonds are the ones that were fitted. And basically, he was like, you need at least 6 bands. Like he had a super crazy high cut of what we wanted to be sure that they were YSOs. Here are just some examples, young stellar objects from the region. So this is a stage 1 embedded source. And I think it's like 2 solar masses or something. But you can see a very nice silicate feature. And the cool thing about MIRI compared to Spitzer is that you have the bands sample things really finely, and they're narrow enough that you can actually basically do crude photometry on, like, does it have silicate or not. So there's a lot you can do just with stellar populations and photometry.
Just
And
a
then
quick
to the right
clarification
is
question.
the yes.
Do you have the Paschen alpha filter with these, or
But we
or
do.
No? Okay.
We do.
Okay. Thanks.
Yeah, I suppose it might be shown here, although he may have excluded it because it's such a narrow band. On the right are the disc-like objects, and you can see again that you have this elevated flex from the disk, but it's also a lot with the star. All right, so I'm gonna move on to NGC 6822, and so this is a dwarf galaxy like the Magellanic Clouds, except it's isolated. We don't think it's interacting with anything, and so it's sort of a different environment. And the Magellanic Clouds are kind of interacting a lot, and the SMC in particular is kind of a train wreck. But this one is pretty pristine, and it is host to some of the most luminous H2 regions in the nearby local universe. And so these Hubble regions out here are actually work done by Edwin Hubble because they were so bright he could see them, from the 100-inch, and labeled them Hubble regions. And they're just massive giant H2 regions. When we were planning this, we didn't have enough GTO time to kind of map the whole thing like we did with the Magellanic Cloud. So we selected regions, and we wanted to study both star formation and evolved star populations because we had an interest in also working on dust evolution models. So with the Spitzer study, we kind of did a lot of homework with Spitzer. We discovered some new star formation regions that are actually at the heart of the galaxy where all the other stars are. And we're like, oh, good. Because originally we were going to do our observations up here so we can get known star formation regions, but you don't get very many evolved stars. So we had to choose, and we found that we can get both if we go to the center of the galaxy, because Spitzer showed us Spitzer I, and Spitzer I has 90 YSO candidates based on the Spitzer data, whereas these other more evolved H2 regions had less. So that was the plan, and you can see the outline in yellow is what we did with MIRI, and blue is what we did with NIRCam. And then here's the NIRCam image. It's just, I love it. I keep trying to figure out a way to get an image that can mount on my wall that brings the clarity of this, and I haven't figured it out yet. But there's just tons and tons of stars, and this is NIRCam only, and then MIRI just of course shows everything dusty and embedded, and then this is sort of where the Spitzer I region was, and this is, I think, a supernova remnant that somebody has to work on. And so with James Webb, we went back to reanalyze the Spitzer I population because we thought, oh, maybe this is like another N79, maybe it's a forming superstar cluster. And we looked at all the point sources. There are 82,000 in Spitzer I alone, just that region. And again, using these color cuts, trying to find the most promising candidates, we found on the order of 130. And then when we start analyzing them, it's not a superstar cluster. It's just super active star formation region at the center. So I don't know if this is analogous to things we find in our own galactic center where you have some central star formation region, but that's where we are on that project. And then Wenswicki 18 is a very famous metal poor but actively forming star dwarf galaxy. It's 18.2 megaparsecs away. It was a subject of Hubble, a lot of Hubble work. And this is the NIRCam image. It can also look like a little jewel box. And this is not north of east to left. This is just the frame. You can see, of course, a lot of background galaxies. And with MIRI, this is what it looked like with MIRI. And of course, with Spitzer, it's just a smudge. I mean, there's no resolution. So it's exciting to be able, and this is like the longest wavelength. So it's like showing where the dustiest sources are. But the 7.7 micron shows you, a pretty good sample of sort of some of the dusty sources, and that's being worked on now. But this first paper that Alec Kirschauer published recently, shows, again, a color magnitude diagram. This is 200, the 2 micron, and then the 115 minus 200. And here we have on the left sort of upper main sequence stars. So really you're tracing the most massive stars in this galaxy when you get this distance, but they're red supergiant candidates. And then as you go to the right, we don't have enough information because we didn't include MIRI in this first round paper. We just focused on NIRCam. So these are probably AGB stars, maybe carbon rich, and they're probably young stellar object candidates in there, and that's to be sorted at the next paper. But just showing spatially, we're kind of so younger is the blue, evolved or stellar objects is in red. So on the left here, you can see where the young massive stars are located. And on the right, you can see where some of these older populations are. And probably here is, and this is oriented north up, piece to the right, is probably young stellar objects around it. But again, we don't have enough information yet. But this is probably an older stellar population down to the left where you might have the AGB stars. It's still young by some people's stellar evolution standards, like AGB stars. I mean, that's a pretty young population, but compared to forming stars. So before I jump on to PRIMA, kind of a very quick summary. So with James Webb's, I mean, one of the remarkable things is you get seven magnitudes deeper than prior surveys, like even some of the optical surveys in these regions. In N79, we have 106 new YSOs with masses from 0.7 to 40, and the most massive is really highly concentrated at the center. I didn't show all the spectra from MIRI-MRS, but we have gas lines, dust lines, and then there was one that had very strong ice features in the paper. It's not that massive superstar cluster, but it's another region nearby. And then 346, first time we see embedded low mass YSOs in extragalactic environment. We see thousands of them, so we can do some good statistics. The Spitzer I source has 130 young stellar objects, sort of more numerous, but kind of lower in mass estimates. And then 1Wiki 18, first dusty stellar population synthesis. I mean, basically, there is very little evidence for lots of dust in 1Wiki 18, and so we're very interested some of our highest motivation is to actually look at the spectroscopy or the crude spectroscopy of the evolved stars to see what type of dust they may have in them. And then, to be hopefully in the next year, we'll have some more papers out trying to show what these are. All right, I want to jump on to PRIMA. So PRIMA stands for Probe Far Infrared Mission for Astrophysics, and this slide shows you who PRIMA is. Basically, these are all the COIs. And then the leadership team's outlined in green, and I'm the deputy principal investigator of PRIMA here. Jason Glenn, who's at Goddard Space Flight Center, is the principal investigator, and Matt Bradford at JPL is project scientist. With these proposals, it's a large partnership of science, but engineering, and the engineering's extraordinarily important because you can have science questions, but then you have to describe what needs to be built, and then you have to show it's feasible to build it. And so these are the partner institutions. So it's a partnership with JPL as the lead center, but with Goddard contributing a lot, and of course they have the PI there. BAE Systems is the new name for Ball Aerospace. And then we have the Italians, part of IPAC LAM, which is in Marseille, and BAE and Esron as international partners. And there's discussions ongoing with JAXA. So what is PRIMA? So PRIMA is a 1.8 meter all-aluminum telescope cooled to 4.5 Kelvin. And so this would be the largest cold telescope. So Spitzer, of course, was cold, and it had, a helium tank. And then Herschel was not a cold telescope. It had cold instruments, but the telescope itself was, I think it's like around 80 Kelvin or something. It was radiatively cool. So the advantage of cooling the telescope is you get rid of the telescope emission. So those of you who do single dish with telescopes from the ground, that's what you have unless you chill your telescope in space. So there are two instruments. There's Primager, which is an imaging and polarimeter. The imaging at the short wavelength from 25 to 80 microns has an R of 10. So it's kind of a hyperspectral. And the thing is to kind of be able to resolve pH emission lines as you take surveys and look for galaxies in the distant universe. And then there's fluorescent spectrometer, and that's an R greater than 85. Now, it really has, the low resolution mode really is more typically around 100 or more. And it covers the range 24 to 235 microns. So the nice thing about the wavelength range is James Webb kind of ends at formally at 28, but it starts getting ratty around 24, 25 because it's got a warm telescope. It's not a 4.5 Kelvin telescope. And so it overlaps well with that. So it kind of picks up where James Webb left off and moves us to much longer wavelengths. And these are critical wavelengths over what you can't see from the ground. And then there's a high resolution mode with kind of the resolution of 4,400. That's at 112 microns. And of course, it scales with wavelength in terms of what the resolution. Longer wavelength, you have changing spectral resolution. And then the detectors are 100 millikelvin cooled kit arrays. And this is, I'll talk about them briefly. This is the sort of the technological wonder that make these missions possible. The data will be at IPAC. It's in Earth Sun L2 orbit. The launch date is 2032 proposed. And observations, the PI led science, which will all be guest investigator science, is just 25% of the mission, but 75% is general observer. So it'll be these probe missions had a requirement of a minimum of 70% being general observer. So they're basically observatories, but PI led and defined in terms of science requirements. So going back to the far infrared detector, so this is why we've had such a revolution in the far infrared. So this is over time, in 1950 all the way up to present day. The noise equivalent power, so this is the noise level of the detectors, has been dropping, you can see, by orders of magnitude over the years. And down here on the bottom right is where we are now. And it's basically, the timing of doing a far infrared mission now is perfect because they've worked so hard on the detectors that it's perfect for a background limited far infrared observatory. And so we have a collaboration, JPL, Goddard, SRON, to demonstrate that the sensitivities that they're getting now in the lab with the detectors exceeds the requirements we have for PRIMA, which is kind of where you want to be because you never know what else will happen in the mission as you put it together. So that's exciting. And then this is what they look like. It's also exciting because you have arrays, because, they used to kind of say, oh, I've got one detector, that was IRAS. And then they start, putting more and more together. PPLS had a few kind of stressed germanium in a row. And now with kids, you actually have arrays. They're not quite CCDs, which has, I don't know, the whole industrial complex behind it, but it's remarkable that you have these 1,000 detector arrays. And this is what it gets you. This is actually showing the predicted performance, but our requirements are kind of much more conservative than this. But this is mapping speed. So this is the time to survey 100 square arc minutes down to this sensitivity level of 3 × 10⁻19 watts per meter squared. So that's the time. So as you go further up, the longer it takes. And then this shows the wavelength range. And you can see PRIMA is here with pink and orange in the middle. And then you see prior and active. So active observatories are ALMA. and James Webb. And so it really fills this important gap between what James Webb can do for us and what ALMA can do for us. And there's a plethora of line diagnostics for local, high redshift, etc. So you can see that even with MIRI, with mapping speed, and a lot of this has to do with the fact that it's a big, tank ocean liner that you're trying to move around. It's not meant for mapping, whereas PRIMA is designed for mapping larger. It's smaller and agile. But there's also, again, this raw sensitivity because it's a cold telescope, and it's amazing how much that buys you. All right, so Astro 2020 talked about far infrared probes, and they said that there are kind of three things you need, or three areas that a probe could address, and PRIMA tries to address all of them in some capacity. It's trying to trace the astrochemical signatures of planet formation. It's measuring star formation and buildup of heavy elements, interstellar dust from first galaxies today, but it's looking at a particular redshift range to look at that problem, and then also probing the coevolution of galaxies and their supermassive black holes in cosmic time. And the thing is, we have this nice relation of black hole and galaxy mass, but then how did it get there is an unknown. Let me just talk briefly about the buildup of dust and metals. That here is a spectral energy distribution of a galaxy of Z of 0, and so you have pH emission, and you go out here and you have these key metallicity lines of O3 and 2. We're using black hole accretion rate of oxygen 6 at 26 microns, and star formation rates with neon 2, because you can probe them all the way from kind of from this local redshift range. As you go further back in time, you can see everything redshift. So everything James Webb had will redshift into bands that PRIMA can address. And then at the longer wavelength range, we have these polarimeters so that we can study polarized emission, and we can actually learn a lot about local dust composition just from polarized emission light. I'm just going to talk a little bit more because there's a lot of people who study disk and spectral formation here. And at the top is just sort of a cartoon of a disk. It's actually half of a disk, right? But just sort of a cut across a disk. And this shows you the region where James Webb is sensitive to, kind of the very inner region. And then ALMA is sensitive to the outer region in terms of what it can probe. And PRIMA is sensitive to everything that's happening in the middle, including these icy pebble drifts. So it's a key wavelength range to understand how disks evolve, how planets form. And then here we have, of course, different types of planets. And if they were to be born at this location, this location, this location, you expect certain P to O ratios, certain carbon abundances, whether they're stellar or more or less than stellar in terms of carbon and oxygen. And so part of the goal is also to understand where did the planets form, but just really understand the disks to even understand the structure and abundances in the disk. And so things that are unknown in planetary formation are disk masses. What is the mass? What are the elemental abundances in the disk? And the water vapor content and distribution. And again, down below is a simulated spectrum of a protoplanetary disk. And you have flex density versus wavelength range. And again, showing the wavelength range that PRIMA or any far infrared observatory would be at covers these water lines, just tons of water lines, particularly cold water lines as you get further out at the snow line. They have, of course, have water ice, and then this HD 112 micron line, which is key for measuring total gas content. And that's one of the, people don't know the total mass because you either measure the dust, you measure CO, but it's frozen out. But HD is a robust indicator of that. But looking at linking the atmospheric abundance of exoplanets to where do they originate in the disk. What PRIMA is contributing here is water abundance, oxygen abundance from water, but it's also primarily this HD line is giving us the gas mass. And in the PI-led science, there's 200 disks that will be surveyed, full spectral coverage at high spectral resolution for this. And this is a cartoon in terms of depletion, but if you looked at a bunch of PRIMA disks and a lot of them were down here, these are C2 depleted disks that would be representative of where something like WASP 77A was formed. Or if it's an oxygen enriched disk, it would be, okay, this is where something like WASP 33B. Completely simulated. We actually don't know what the answer is, which is why we need the mission. And then I think some of you work on supermassive black holes, and so that is one of the other science objectives, is to look at the scaling relationship between black hole accretion rate and star formation rate. On the left is this nice cartoon I described, where you could have, depending on your model, you could start down here with higher stellar mass, and then you become a supermassive black hole, or maybe you have a larger black hole mass, and you have different paths. And on the right are just two different models: the Santa Cruz semi-analytic models at the top, and there's Spitzer on the bottom. And when you go over redshift range, we don't really know what happens at the peak epoch of star formation in the universe, where a lot of things are happening. And so with PRIMA, we'll get these accretion rates, the black hole accretion rate to star formation rate over redshift through the peak epoch of star formation, and get some clarity on which type of model is.
3 minutes, it's okay.
I am just about done.
That's great.
So geo science again is 75%, and we hosted a couple of online workshops to just find out from the community what they would do with the sketch PRIMA. And so this is a geoscience book that Ariel Millay, that NREO here led for the lead editor of. And there's 76 cases, and it's posted on the archive. And then again, just as a little snapshot of the types of cases. We got people wanting to do concept objects and energetic phenomena, kind of doing time domain work. Some people want to do cosmology, galaxy studies a lot, Astrosolar project, and then ISM star and planet formation, of course, quite a lot, and then just even stars. There are cases. So it covers all of astronomy. And then just like, what can you do with PRIMA? And, in 1200 hours, you can measure the D to H isotopic ratio of water in a statistically significant sample of comets. And then 100 hours, PRIMA can just map magnetic fields, lots of local galaxies, star formation. And then someone put in a case of measure the whole sky, and that was 5,000 hours. I mean, these are not, I mean, again, these were just ideas that came up, and but it was kind of cool to see that there's a lot of energy and interest. So again, we addressed all three science goals for the Farm for Perth from the decadal. We have the technology in hand to actually make this happen, and then it has a broad science graph and large community interest. And really, the future Farm for Astronomy is in your hands. Step 2 announcements will be at the end of calendar year. There is a special session at the AAS. So I know a lot of you are going. If you want to throw in an extra poster about foreign infrared astronomy, you can have an extra poster. How these special sessions do. And I encourage you to submit an extra abstract. And I will see you there. And there's an IRSDIG meeting that they're planning May 5th and 7th in Washington, D.C. in 2025 to kind of, we'll know the results by then and discuss things. So thank you. Thank you for your time.
Great. So now we have time for questions and discussion. And so raise your hands in the Zoom if you have a question, and and just here, speak loud for the microphone, please. So, Devesh,
hi, excellent talk, Adam. I was just wondering, for the N79, you showed a couple of massive stars.
Yes.
If you could please go back, I have a lot of, it's so cool. I have a few questions. I was just wondering, these massive stars, we are very certain that they are indeed pre-main sequence objects, huh?
Oh yes. Oh yes. Yeah. These sources.
Sorry, where we had the spec. Yeah, that's the one. Yes.
Yes.
And so for the 40 solar mass, you have this like broadening of lines, and I was wondering what for the 40.
Oh, not this one. This is Spitzer. This is,
Ah, okay.
no, this looks broader because the resolution was 100 as opposed to 1,000.
But can you comment on how these masses come from SCD fitting? Is that right?
It is from SCD fitting, yes, yeah. And so there are uncertainties, and we have done. There was one of the cases years ago when we studied and did SCD fitting of like the region, and then we looked at like HR diagram type stuff, and so the masses could be higher, honestly. Yeah.
And then you just
light leaks out, and you don't get all of it.
and then you briefly mentioned any idea on the accretion rates, what you're seeing here?
Oh, in the paper, so look at the NIAC paper because she has the accretion rates for all of them in there. Yes. I just can't remember what they are off the top of the head, but that is the thing she measured for all the sources.
Ruben, you have a question? Do you want to go next?
Yeah, sure. Well, first of all, thank you, Margaret, very much for the nice talk. I'm from Granada, and I'm wondering actually in this same study that you show this color diagram
Yes.
where you show YSO candidate with and without Paschen beta emission. Can you comment a bit more on that? Like, first of all, how do you know that they're YSO? I guess it's for the color, but how do you explain this YSO without Paschen alpha, not Paschen beta, emission? Because these hydrogen emission lines may come from accretion, from ejection.
Right.
How come they don't have any Paschen alpha?
I mean, that is a good question. I mean,
They just stopped accreting, have
they
they?
could either have. We have not studied them. I mean, what we've done so far is just used it to identify things, but we haven't gone back. I mean, Guido has gone back to look at some of the pre-main sequence stars, and then looked at the Paschen alpha with like near spec, where you really cleanly measure the Paschen alpha emission. This is the narrowband passband, and so the idea is, while it could be excess Paschen alpha, quite possible, but it could also be just reddening. So I think it's TBD actually what the net Paschen alpha is. So I wouldn't put too much weight on with and without at the moment.
Right.
It needs to be like externally ionized low mass disks, because I know when in like the
Right.
Orion star region,
Right.
any Paschen alpha that's say over luminous than what's predicted by its central star, we call that a photoevaporating disk. So I'm wondering if
Oh, do you?
I'm
Okay.
wondering if you're seeing these in these distant low metallicity regions, if there's any hint of that with this
Well,
Paschen alpha.
I think possibly.
Yeah.
I think with the spectroscopic survey, the subtraction. I mean, some people also, well, it's an ambient, like it's
Yeah.
an environmental, and actually not the star. I think with the spectroscopy, it's very clear that it is with the star because they have a spectra off the source of just the nebula, and they subtract and make sure that the net is net. They used to do a background subtraction. But you're right. I mean, is it optically thick, and are you being irradiated, and how much? That's an interesting question.
Just one more follow-up on that. Are there line widths of the Paschen alpha for any of the low mass where you have the spectra in addition to the near cam?
I think in the first paper, and that was accepted. I think it might be. So it's the marking. I think that was the low resolution mode.
Okay.
So I don't think it's.
Yeah.
I think it's unresolved. But we do in our follow-up. I think we did higher spectral resolution. So the new data that we're playing with might have. And you're just saying, is there a width? Can we measure the width of the line?
Yeah, because with the externally ionized scenario, you would expect line widths around maybe 30 to 50.
Okay.
And if it's maybe from the star, it'd probably be more like 100. So that might be a interesting discriminant.
No, that is good to know.
And just following up on the diagram you have here, I recall another diagram where you mentioned that there is this possibility of being confused with AGB stars and YSOs, but here they seem all quite separated. But in your other diagram, they were mixed. Can you comment a little bit about there's potential confusion with AGB stars.
Right.
We have some projects in the galactic census, Sam's project in particular, where we'd like to find YSOs, but we aren't sure we can find them. So
Right.
how do we do
I
it?
mean, in this particular case, we're looking at a really young massive star formation region, and the nearby stars, that stellar population, are basically at the age of globular clusters. So there's like very low concern for AGB contamination in this region. But when you go to a whole galaxy, you worry about this. Like the YSOs and the AGB stars here, there's a student working with Libby Jones looking at the AGB population, and he's going through trying to find the AGBs, and he's finding, well, I think actually some of these are YSOs. So Laura's working with him to kind of sort that out. So what you need to do is fit them with YSO models and AGB models, and do both of them, and then sort out which one's the best fit. And that's how I would suggest going about that problem. And then here again with one's Wiki 18, these are just the near infrared bands. The longer wavelength you have, I mean, usually the YSOs continue to rise. I mean, they peak probably at 50 microns if you could. Whereas AGB stars tend to peak, the really dusty ones may peak at 10 microns the most. Maybe you'd have some weird ones that would go a bit longer, but they tend to turn down at 20 microns. So I don't know what wavelengths you have for your candidates, but if you can at least get a 20 micron band, that'll help. It'll go up if it's a YSO, it'll go down if it's an AGB.
Mirror imaging then, yeah.
Oh yes, you'll need mirror imaging, yes.
So I was going to say then, is there a degeneracy then between AGB stars that will peak at like 10 to 20 microns and then tail down with like later stage YSOs where their disk is dissipating and their far infrared tail is
There
receding
could
back?
be. I suppose there could be. I mean, there you'd have to look at some ancillary data, but that has always been a confusion of the evolved stars. And then actually planetary nebulae look even a little bit more like YSOs than AGB stars. So you always have to worry about that contamination.
Right, but it sounds like it's model dependent and degenerate, so we may struggle.
A little bit, but right. So you can always say it's a candidate, but then you follow up, you get spectroscopy. When you get spectroscopy, it's pretty clear. I mean,
Yeah, I wanted to ask about the IMF, but I noticed Ruben had another question, but was that related, Ruben?
Yeah, it was a follow-up for the Passion Alpha, and I wondered if you had bracket alpha observations that maybe you have counterpart with the Passion Alpha or not. Maybe those with no Passion Alpha observed would be observed with bracket alpha just because of extinction or not. Do you also have bracket alpha or?
no, we don't have an air band for it, but we
Right.
Do have in our follow-up near spec follow-up, we have the whole band of near spec. So for, I don't know, we have maybe 80 sources, 15 of which are like embedded YSOs, but so we have lots of data on those. So
Right,
you can
right.
probably figure out accretion rates and things for those.
Because in our case, I mean, Jonathan mentioned about SAN's project in the Galactic Center. We cannot have Passion Alpha observation. I mean, we can try, but it's at the Galactic Center very, very embedded, and we rely on bracket alpha. But it's not that we have a ton of bracket alpha access, to be honest. I mean, Sam can comment more on that. And I was just wondering how we can, as Jonathan just said, find YSOs in our images, but it seems to be hard. At least we need the spectroscopy.
I think that's, to completely nail it down, yes. But I think you can do a lot with
Right.
geometry with James Webb without resorting.
Thank you.
Yeah, would you want to ask your question?
Sure. Just have you been able to put together IMFs? Do they vary among these low metallicity sources? How do they compare to like galactic star?
Great. Yeah. I mean, that is something that, so for 346, there's a student in Dublin who is now doing the ultimate catalog. Like he's going through the whole catalog, and there'll be a catalog paper, and then he's studying why. So the hope is that he will be able to do IMF studies. I think he's focused a bit more on the young stellar objects, but just even looking at the stars, I mean, we believe we'll be finding brown dwarfs, be able to sample down to a brown dwarf limit. I don't know to what completeness,
For all four regions, or all four targets, or
Certainly for 346 and N79. We go deep enough for that. The group is kind of focused on finding the young stellar objects, but but the catalogs that they're producing can be used for that. And the student in Dublin may do an IMF study. I mean, certainly with the YSOs, they'll do an IMF study, but just looking at the stellar population.
Well, I thought somewhere I saw that the lowest mass you're probing is 0.6 solar masses.
That's with what we have now with MIRI. But it'll with the NIRCam results, you go down much lower. Yeah, right. Just in terms of stellar photospheres.
Yeah, if you can measure the peak of the IMF in particular, that would be great.
Okay. And you're just looking at the star cluster and just like the population of the stars, not even of the newly forming stars.
The IMF we have done is they're mostly dust free, I think.
Dust-free.
Relatively dust free.
So there will be opportunity to do it. It may be a different group that ends up doing it just because of bandwidth issues, but certainly the data will be there. And it's an interesting question. There have, of course, done studies in the Magellanic Clouds and IMFs, but typically, on the more optically bright, and they all look like the galaxy. But it's a question of when you go down to brown dwarfs, that's the part that hasn't been studied so much and is maybe the more interesting question.
I want to ask a question about PRIMA as well. What do you expect the angular resolution of PRIMA to be?
It'll be diffraction limited with a 1.8 meter, and so it's a few arc seconds.
Okay. So I guess then
it's not going to have the clarity of James Webb.
Yeah.
No.
So I guess it'll probably be best for just, in the case of the disks in the water, probably just the closest ones, because I guess the further you go, you won't be able to resolve individual disks from each other,
Well,
maybe.
Yeah, I mean, having, I suppose, something isolated, but you're not going to be resolving spatially.
Yeah.
This.
Yeah.
Unless you're looking at like Vega or something where you're looking at the debris disk, in which case you resolve it. But it's mainly the spectroscopy that helps you a lot. And then in terms of looking at the structure, the plan is to use all the lines, because you're going to have hundreds of lines to model the structure of the disk. And then at the shortest wavelength, you actually will spectrally resolve the water lines.
Okay.
Because you have higher, like 20,000 resolution, but at 24 microns.
Okay.
And then as you go to the long wavelengths, they're unresolved, but then you get the cold.
Right.
Joe, if there are questions in the green room, shout out. But I was going to continue PRIMA questioning as well. Can you remind us, Margaret, about the polarization? Then you said it briefly. Is it across all the wavelengths you have polarization?
It is the longer wavelengths. Right. So the polarimetry is R4 imaging and polarimetry 91 to 261 microns. So that's the wavelength range, and they're maybe the baseline design is 4 bands, and I think to meet the science goal you need, I think, at least 2. You can get away with 2, but right. So there'll be 4 bands. Actually, in the Geo book, there were a lot of people, because of the Hawk Plus results that were coming out. There's a lot of interest in doing polarimetry.
And you're the only mission that does polarization, is that?
Yeah, I can't speak for the X-rays, but amongst the foreign missions, yeah, I think we're the ones that did sort of an imaging polarimetry. A lot, yeah.
Sorry, I wanted to ask, how does PRIMA compare to some of the other foreign
proposals?
Yeah, that are being proposed. It sounds like polarimetry is
polarimetry is something we do. Our spectrometer focused on getting the whole band coverage. I mean, that was an important goal. Certainly, some of the science requirements required that, and some of the other missions went more for higher spectral resolution. So they resolve the disk and get they call it Doppler tomography to get the structure of the disk with that approach. I think first takes that approach. Saltus also has had a spectrometer, but then it also had a heterodyne spectrometer, which is, ALMA resolution, right? First, the size was similar to what we have with PRIMA, but with Saltus, they have a very, they have a spectacular telescope that just opens up to like a 14-meter. And then, does spectroscopy, and I think it's mostly spectroscopy. I think there is some imaging, but I actually, if you, in my backup, I was trying to think, don't I have something? I said, yes, in your backup. So you actually have a little synopsis of the other mission. Okay, so this is first, right? So this is what first is, just a one slider on it. The DDSI, so their spectrometer is quite capable, going from 100, but then up to 100,000 for some key lines. I mean, the trade-off you have with spectrometer is high spectral resolution, going over, a few regions. I mean, that's what heterodynes do, or you go for it all. It's, it's a trade that you base it on science. And they have our 20,000 in this long wavelength range. And then they have this HSI, which again, that's right, they have heterodyne mixers. So super high spectral resolution, 10 to the 6, 10 to the 7, 5-pixel dual polarization. So it's a heavy spectroscopy instrument, but we've had, the argument might be, well, you have some imaging and now you really want to get spectra, and it's a probe. It's not, it's not a great observatory class. You have to make choices. I mean, you have $1 billion cost cap, and you have to choose. Saltus, so this is PRIMA, which I talked about. Saltus, there's some similar key objectives. I mean, everyone is interested in the formation of planets. That's a key part of all of these. But here's this 14-meter inflatable. It's passively cooled, so it goes to 45 Kelvin, not 4. And then they have 2 spectrometers. This is Safari Light. So, I mean, one of the wonderful things about this probe competition is there have been similar size competitions in Japan and in Europe for like, I don't know if anyone heard of Spica, but Spica was like a big push. And when we were working in the Origin Space Telescope study, we thought, okay, that's the big class, Spica's moderate class. We all thought for sure Spica was going to go forward. And then when it fell apart, it was just shocking because it didn't seem rational, because they were in the competition. They basically were in step 2, and they just said, okay, you're no longer competing. But because of all the science and technology buildup for it, I mean, all these far infrared probes got to take advantage of all that work. So the work on Spica wasn't wasted. It was just, put behind. Yeah, it was reshuffled, put behind the U.S. leading it now, and cross our fingers we get it. All right.
I think we're out of time. We've been warned we're going to be kicked out of this room as
Okay.
well. So let's thank Margaret again for a great talk and discussion.